Welcome back to week 5. We're going to begin something completely new from this week onwards. We're going to look at software testing, test case design, but our focus is not going to be about looking at graphs. We're going to start looking at the relational and logical expressions that come as a part of decision statements in the code, if, while, for, switch case, and so on. You have plenty of decision statements that give rise to different execution paths in the code. We're going to focus on those logical decision statements and learn how to design unique and different test cases based on them. If you remember when we did graph-based testing, I had first gave you an introduction module on just graphs. So that's what we're going to do today. For the next 2 weeks, 3 weeks, we're going to look at logic coverage-based testing. But before that, it helps to understand the basics of mathematical logic, logic as we see in discrete maths. So today's module is just going to help you recap the basics of logic. And if you don't know it first, this module will be a complete module that will teach what mathematical logic is all about. Logic is a very, very old area. Formal logic, as is used in mathematics and subjects like philosophy and computer science now, dates back to 320 BC. So you can imagine how old it is. What I'm going to do in this half an hour lecture is to provide you a very cursory introduction to this very vast areas. But we're going to focus on understanding the very basics, specifically propositional logic, and what we need to get started for using it in testing. The fragment of logic that we will consider in this course, for that matter, all software engineers, programmers and testers would consider, is called predicate logic or first order logic. And the basic entities there are the components that constitute your relational logical expressions, function calls and stuff like that. We call them as predicates. And in general, if you refer to a book in logic, predicate logic will have formulas that have quantifiers like for all and there exists, but we work with quantifier-free logic in this course. And for that matter, throughout software testing. So let me begin with the basic, most fundamental logic. We may not use this logic in the course, but it sets the foundations of what logic is all about as it's used in maths and computer science. So what is such a fundamental logic? It's called propositional logic or Boolean logic, as many books or hardware engineers would call it. The same thing sits on hardware circuits also as gates, but we will look at it from the point of view of computer science. So the basic constituent entity of a propositional logic is an atomic proposition. An atomic proposition is any term that can evaluate to true or false. For example, here is an atomic proposition. New Delhi is the capital of India. So this term as a sentence constitutes one atomic proposition, and its proposition in the sense that it is true. Sometimes it can be false. Like for example, the third entity given here, 3 plus 3 is equal to 8, makes a statement that is always false. Whereas the last one, today is Friday, is true on all days that are Fridays and is false otherwise. So atomic propositions are the basic building blocks of any logic, specifically propositional logic. What is an atomic proposition? An atomic proposition, also called as a proposition, is just a declarative sentence or an expression that can either return true or false at a given point in time, but you will never get a fuzzy answer about I don't know whether it is true or false. It will always be either true or false. The truth or falsity can vary as time varies, or the truth or falsity can be standard. But it's a statement that will always return a Boolean value, which is true or false. This constitutes the basic of propositional logic. So as I told you, this is atomic proposition. In propositional logic, we take this atomic proposition and combine it with what we call logical connectives or operators And then we form formulas. So the terms that you find in blue color in this slide or in the slide deck are formulas or terms that you must understand. They are new and they are specific to logic. So propositional logic takes these atomic propositions and uses these connectives to form what we call well-formed formulas or formulas. For example, OR, which is written using this symbol that resembles a V, also called disjunction, is one Boolean operator connective, takes two operands, and which is written like a wedge, which represents conjunction, represents another connective. Not for negation is a unary operator that takes one operand. Implication, which can be written like this or like this single-headed arrow, is another binary operator. Equivalence is another operator. Like this, you can have XOR, NAND, NOR, and so on, several different operators. So I take these atomic propositions, which can either be true or false, and combine them with these kinds of operators. So I can take an atomic proposition P, another atomic proposition Q, and combine it and get a formula called P and Q. I can also get another formula, say not P or Q. Like this, we can form several different formulas. So we assume that we have a set of atomic propositions, as many as we want. So this set is countable and we have as many as we want. So it's an infinite set. And how do I form the set of formulas of this propositional logic? Every atomic proposition by default is also a formula as a standalone single entity. If alpha is a formula, then I can stick a not in front of alpha and I say negation of alpha. Read here this part where my mouse is pointing to as not alpha. The symbol is to be read as not or negation of alpha. So if alpha is already a formula, then not alpha is also a formula. If alpha and beta are formulas, then I can combine them using an or an and, or an if and only if, and get new formulas. In this case, I have combined them using an or. Similarly, I can combine alpha and beta using an and it so happens that alpha and beta is equivalent to this one that you see on the right side of the column. How do I read this? It might look long, but you can practice reading it. So it is negation or not of not alpha or not beta. So alpha and beta which is two formulas, alpha and beta combined together with an and, happens to be equivalent to not of not alpha or not beta. Similarly, I can take some other alpha and beta and put them alongside of an implication. Alpha implies beta can again be expressed as not alpha or beta. Similarly, if and only if alpha, if and only if beta, or alpha equivalent to beta can be written as alpha implies beta and beta implies alpha. You don't have to worry about how we get these equivalences. This is just to tell you that these two basic operands, not and or, are enough to create a whole set of formulas in propositional logic. So here are some examples. Suppose you had a condition like this. One cannot ride the roller coaster if you are under 4 feet tall unless you're older than 16 years. I can naturally express this as a formula in propositional logic. Let's see how to do that. There are three parts to it. One is riding the roller coaster. The other is how tall one is, being under 4 feet tall or more than 4 feet tall. The other is how old the person who wants to ride the roller coaster is. He can ride, he or she is older than 16 years. So there are the three constituent atomic propositions. You can ride the roller coaster, you are under 4 feet tall, you are older than 16 years. Let's call them as Q, R, and S respectively. Then what the sentence says can be expressed as a formula given here. R, which means you can ride the roller coaster. Q, which means R, which means you are under 4 feet tall. And if you're not older than 16 years, implies not Q. You cannot ride the roller coaster. Let me read it out once again. R, substitute for R as you are under 4 feet tall, and not S. S is you're older than 16 years. Not S means you're not older than 16 years, implies not Q, which means you cannot ride the roller coaster. That's what this sentence says. What we have done now is express this sentence as a formula in this logic. One more example. Maria, a student, will find a good job when she learns software testing. I want to express this as a formula in propositional logic. There are two parts to it. Maria learns software testing. Maria will find a good job. So if Maria learns software testing, which is P, then it implies Q, where Q means Maria will find a good job. So I can express a sentence like this also as a formula in propositional logic. So like this, I can express several different things. Sentences, properties that are true about software, properties that are false about software. Several different things can be expressed as simple formulas by assigning appropriate atomic propositions to each individual component. Now, this is how I create formulas. This is what we call as the syntax of propositional logic. I have a set of atomic propositions, as many as I want. Then I can use these operators not, or, and, implies, if and only if, to create formulas that look like this as far as applications are concerned. The next natural question to ask is, what is the semantics? What do these formulas mean? Where do they hold true? Where do they hold false? How do you do that? So for that, we need what we call a valuation, which is basically a function which takes each atomic proposition. Remember, P is the set of atomic propositions here. So it takes each atomic proposition and returns true or false. T for true, F for false. So a valuation is a function that tells you for all the atomic propositions that you are using, whether it is true or whether it is false. Like, let me go back for a second. Look at this. If this is an atomic proposition, New Delhi is the capital of India, then a valuation function will tell you this is true or false. In this case, it happens to be true. If you take the last one, today is Friday, as another atomic proposition, a valuation function will tell you that this atomic proposition is true on all days that are Fridays and false otherwise. If 2 plus 3 equal to 5 is an atomic proposition, then a valuation function will tell you that it is always true. Similarly, if 3 plus 3 equal to 8 is another atomic proposition, then a valuation function will tell you that this is always false. So a valuation takes a function, is a function that takes an atomic proposition and tells whether it is true or false. We extend each valuation V to, this is for every atomic proposition. Now using atomic propositions, we created formulas like this. R and not S implies Q, P implies Q, more such complicated formulas. How do you know whether the valuation will make them true or false? So we start using the meaning of the operators. For example, suppose I had a negation, not. Not beta will be true as per a valuation if and only if the valuation assigns beta to be false. So if alpha is a formula that becomes not beta, then the valuation of alpha will return T for true if and only if, this IFF stands for if and only if, the valuation makes beta false. Similarly, if I have alpha, which is a formula of the form beta or gamma, then the valuation function will make alpha true if and only if it makes beta true or gamma true. Is this clear? So it's the usual meaning of not, or, and that we attribute in our daily life. Not beta is true if beta is false. Beta or gamma is true if beta is true or gamma is true. Similarly, you can go on for and, implies, equivalence, and so on. So there is an algorithmic way of calculating when a particular formula returns true or false, and that is done using an entity called truth tables. Truth tables represent a simple algorithmic way of calculating whether a given formula will return true or false. The way it works, takes the formula, breaks it up into smaller and smaller and smaller parts till we reach each individual atomic proposition. Then it makes each individual atomic proposition true and false in turn, assigns the meaning of all these operators like not, or, and uses the meaning of these individual operators to evaluate the formula. So let me give you how the truth table for simple formulas look like. So here is the truth table for negation. So how do you read this truth table? On the heading of this table, there is one column for P, one column for not P. The column for P, two possible truth values are given. Row 1 says P is true, row 2 says P is false. T for true, F for false. So when P is true, negation of P or not P becomes false. That's what is given adjacent to that. When P is false, not P becomes true. Is this clear? Similarly, when I have P and Q, how do I know when P and Q as a formula is true? So assign possible values. So break up P and Q into two parts. P is one part, Q is one part. Assign possible true-false values to each part. How many combinations can be there? These are the four combinations. Both P and Q become true. One of P and Q become true and false. They take turns. P is true, Q is false. P is false, Q is true. Both P and Q become false. Is it clear? And then see what happens to AND. If both P and Q are true, then the formula P and Q will also be true. But in the cases where one of P and Q is false, or both of them are false, which represents rows 2, 3 and 4 in the table, in all the three cases, P and Q will return false, which is marked by F. Similarly, we can come with the truth table for OR. Again, four combinations for P and Q exist. True, 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 false, false, true and false, false. P or Q happens to be true if at least one of P or Q is true. So those are the first three rows. If you see in the first row, both P and Q are true. So the whole formula returns true. Second row, P is true. So the formula returns true. Third row, Q happens to be true. So the formula returns true. Last row, both are false. So P or Q becomes false. Next is implication. P implies Q. P implies Q means whenever P is true, Q will also be true. Is it clear? So first case, P and Q are both true. So P implies Q is true. Second case, P is true, Q is false. So it violates the condition that whenever P is true, Q is true. So P implies Q will return false. Is that clear? Third condition and third row and fourth row, P is itself false. So we don't worry about Q being true or false. Both the cases, because P is itself false, we say P implies Q is true. P equivalent to Q says P and Q take the same values. They both can be true together or they both can be false together. That's what this truth table represents. If you see the first row, both P and Q are true together. So P implies Q is also true. If you see the second and third row, between P and Q, when one of them is true, the other one is false. So P equivalent to Q returns false. In the last row, both P and Q are false. So they take the same value. So P equivalent to Q returns true. Is it clear? So these are truth tables for the 5 basic operators. We use these truth tables to get the truth table for the whole formula. So let's see that as an example. So suppose I had a formula which says R or S or not Q. You should slowly get comfortable with reading these formulas with the symbols. How to read this formula? R or S or not Q. So break it up into smaller and smaller parts till you reach atomic propositions. What are the atomic propositions here? R, S and Q. And then there is R or S. And then this R or S is combined with another OR operator and a not Q. So I have these rows in the truth table to start with. These columns, sorry. One column for R, one column for S and one column for Q. and I write values. In the first row, all of R, S and Q are true. In the second row, R and S are true, Q is false. Third row, R is true, S is false, Q is true. Fourth row, R is true, S and Q are false, and so on. Now use this truth table that we saw here for R, the one that you see on top for R, to evaluate this part, R or S, where you focus only on this row. Use the truth table for R. R or S becomes true if at least one of them is true. So a whole set of rows will be true. And finally, when both of them are false, it will be false. Now use the truth table for not Q, which we are not writing here for simplicity's sake. And then use the truth table for R or S ORed with not Q. And this is the final thing. So take this column for R or S. Take the negation of this column, third column for not Q, and use the truth table for R to get this value. So this is how we check whether the formula like this is true or false. So this is a formula in propositional logic. This formula gets true in all these instances, first 6 times and in the 8th time, and only once it becomes false. So for example, it becomes true when all of them are true. It becomes true whenever R is true and whenever R or S is also true. It becomes false only in the case when R and S are false and when Q is true. Then not Q will become false. So the whole thing will return false. So this is how I use truth tables to find out instances where formula is true and where a formula is false. Same thing like we do for programming. If I have a predicate labeling an if statement, sometimes the if statement evaluates to true, sometimes the if statement evaluates to false, based on the individual constituent true-false values. So now, if there is at least one instance where a formula evaluates to true, then we say such a formula is satisfiable. A formula alpha, it could be a formula like this, R or S or not Q, is said to be satisfiable if there exists a valuation V such that V of alpha returns true. We use this mathematical symbol V satisfies alpha to indicate that V of alpha is true. On the other end, if a formula always returns true on the truth table like this, in the column corresponding to the formula, if you have only true values, then we say that the formula is always valid. In logic, we call them as tautologies. The formula alpha is said to be valid if for every possible valuation, that is every possible true-false combination, the valuation will always return true on alpha. For an atomic proposition P, the formula P or not P is valid and the formula P and not P is not satisfiable. You understand, right? Between P or not P, one of them will always be true and OR will be true as long as one of them will be true. So this is an example of a valid formula or a tautology. On the other hand, take P and not P. Between P and not P, one of them will always be false, and because they are combined with an AND, the whole formula will always be false. So this is what we say, something that is not satisfiable. It is also called a contradiction in logic. So there is a small result that you can prove. I am not going to give you a proof that a formula is valid if and only if not alpha is not satisfiable. This is a simple truth in logic. So to check if a formula is satisfiable, we like satisfiable formulas in testing. Why? Because they label if statements, while statements. Sometimes we want them to be true, sometimes we want them to be false. On the other hand, if a formula is valid in this sense, they always become true or is not satisfiable, which means it always becomes false, then there is no use of that formula labeling an if statement or a while statement. So we like satisfiable formulas. So how do you check if a formula is satisfiable in logic? Way to do it would be to construct a truth table as I showed you in that example and check if there is an entry that makes it true. Even if you find one row, like in this case where the formula returns true, then you know that the formula is satisfiable. If all the rows return true, then also the formula is satisfiable, but it will be valid also in the sense that There will never be an instance where the formula becomes false. We like formulas that are sometimes true and sometimes false in software testing or in general programming, because that's what we will use to label the if statements, while statements and all that stuff. So this algorithm based on truth tables is actually an expensive algorithm, because if you have 3 propositions here, you get 8 rows for the different combinations of true false values. In general, if you have n atomic propositions, you'll get 2 power n rows. So it takes exponential time to generate the truth table, and in general it's an intractable problem. It's an NP complete problem, as we call it in computer science. Don't worry too much if you don't know what NP complete is. This is not needed for the purpose of this course. Just wanted to tell you that this problem doesn't have an easy algorithm. It just has algorithms that take an exponential amount of time, a long time. Now, this was atomic propositions and propositional formulas. But in programming, we use not only true false values, we use a whole set of other variables. We use functions, we use relational operators like less than, greater than, we use variables of integer type, we use functions that return something, we could use strings, we could use floating point numbers, several different things. So, atomic propositions in propositional logic can be compared to variables that are of type Boolean in programming. That's natural. While talking about properties of programs that manipulate data, we not only look at Boolean variables, we look at whole set of other variables, and we discuss values of variables that come as the program executes. So we have to go outside propositional logic and look at general variables and what are the values they take, to be able to combine with and or not kind of operators for us. So in general, we say a predicate is any expression that evaluates to a Boolean constant. That is, it always evaluates to true or it always evaluates to false. For example, x greater than 0 can be a predicate. Based on the value of x, x greater than 0 will return true. If x is negative or 0, x greater than 0 will return false. So predicate can contain variables of type integers, floating point numbers, strings. It can contain functions that return some value and so on. Variable types can be anything, as I told you, integer, floating point number, arrays. They are broadly classified as Boolean and non-Boolean. If it's Boolean, we can use them as first-class entities in a predicate labeling and if for a while. If it's non-Boolean, we use it as a part of an expression that returns a Boolean value. Is that clear? That's what we do. So like you take this, variables as I told you can be integers, reals and so on. They can be combined with relational operators like this. Less than, greater than, less nor equal to, greater nor equal to, not equal to. For example, here is a predicate. Look at the last item here. X is greater nor equal to y, or negation of flag, or f of x. So x is greater than or equal to y is the first part, or is the logical connective. Not a flag is the second part, or is another logical connective, and f of x is a function. And because it's combined with an or, the function f returns a Boolean value. Is this clear? So here x and y could be of type integer. X greater than or equal to y will return true or false based on their values. Flag is itself a Boolean value, so I can use it like flag or not flag. F of x is a function which returns a Boolean value. So these three individual things, or even things like x plus y less than or equal to 5, all those things are predicates. We take these individual predicates and combine them using logical operators like and, or and things like that to get additional predicates like you see here. One more small notation as we move on. While we call these entities x greater than or equal to y or not flag or f of x as predicate, it has three parts, and each individual thing we call it using a special name called a clause. So for the purpose of testing, we consider each part of a predicate that is not contain any logical operator as a clause. A clause is a special kind of predicate that does not contain a logical operator. For example, suppose I had a predicate that looked like this: x greater than or equal to y, or not flag, or f of x. Then this one has three clauses. The first bit, x greater than or equal to y. Second one, not flag. Third one, f of x. Clauses are joined with operators like and or not to get larger predicates. Clauses themselves are like smaller atomic predicates. Is that clear? So now our goal, we might have expressions like this: x greater than or equal to y, or not flag, or f of x, labeling our if statement or while statement. Ideally, to test them, we need one values for all these variables that makes the whole predicate true, and one set of values that make the whole predicate false. So we're again looking at what we call satisfiability problem. The whole predicate must return true, whole predicate must return false. But now the complexity is x, y, f of x. They are all not atomic propositions. They are variables of their own types. So we say that a predicate is satisfiable if there is an assignment of values to its constituent classes that makes the predicate true. While we saw that for simple propositional logic, the algorithm will take a long time, exponential time, it so happens that for predicate logic, sometimes the algorithm will not even stop. So we call these problems as undecidable problems. So, but not to worry, we won't really look at all these mathematical or core computer science concepts. We will use things like SAT solvers or SMT solvers that will check as black boxes, third-party tools, whether a given predicate returns true or false. Down the line, I will tell you more about what these solvers are. So I'll stop here for now. We'll continue with logic-based testing the rest of this week and next week. Thank you.